Blood typing and hemolytic disease in the newborn. This is a lab-only lecture, and when I finish it, assuming that we have time, because this takes me some time to practice, we will finish our molecular techniques. I'm giving you this lecture because next week you will be playing with my blood. I will be asking a previous student of mine, to come draw my blood. We have you blood type my blood, and and I hate this part of my job, before I give all of my blood, I would like you to know how best to work with it so that we don't waste one drop. Because he's only poking me once, and he will take a lot of tubes of blood from me because I will supply blood for all of the other physiology sections. Yeah, it's not a part of my job that I like. Blood typing is an immune reaction. That is what we are manipulating. And up on the screen, you are seeing an immune response in the left picture. Can you see the clumpiness? Can you see the blue picture and all the clumps there? That is an immune reaction. Over here, that reaction is not occurring. You don't see the clumps like you do over here. The blue part is not important. That's non-consequential. That is just part of the antibody solution that you add. So the blue, the color difference, that's not what you look at. It's the clumps that you see. In order for this immune reaction to occur, you need two things. If any one of these two things is missing, the immune reaction cannot occur. The two things that are required is one, an antibody, and two, an antigen. How many of you have taken micro? Okay, so this lecture and lab will be very boring for you because you already know what antibodies are and what antigens are. But for those of you who have not taken micro, these might be new terms to you, or you might have heard of them, but you don't really know what they are. So we need an antibody and an antigen. I'm going to tell you what an antigen is, and I will also tell you what antibodies are and what cell in your body makes them. When we say, what is your blood type? When we ask that question, it is really what we're asking is, what antigen do you have on your red blood cells? That's really what we're asking. What antigen do you have? So my goal is to teach you the antigens that we find on red blood cells. There are many, but there are some that we focus on more clinically. So that's your ABO blood types, right? How many of you know your blood type? Okay, those of you who don't, would you like to know? Because next week, if you want to find out what you are, you can blood type yourself. I will let you. Okay, you do not, it's not. She's like, no, I don't need, it is not that bad. I have, it's not going to be that bad. I think when okay, I hear you. I've been told by the Red Cross not to come back to donate blood. I've been told that I can serve the community in other ways, but not donating blood. And I'm here to tell you that you can use this. Just a little prick. It hurts less than a paper cut.
Yeah, I don't know why. I think the anxiety.
Yeah, I'm telling you, so many things, it's not bad. And everyone's like, oh no, it's a little lancet. Little lancets. I'll teach you how to put it. There's one up there. As your that is not okay. Oh my God. See, that's horrible. Who leaves this loaded? I was playing with it, crying out loud. That's not okay. That's how I Oh my God. That's not okay. Whoever did, I don't know who did that. That's not okay. I have students who have HIV. That's not okay. Anyway, yeah, that is scary. That should not have happened. I'm glad it was me who found it. But we take this, okay, we put it in here, and it's a spring lock mechanism. You'll put it like this, which is what I was doing. And when you hit this button, this little needle will go chirp, and you then squeeze, and you get out a little piece of blood. It's gonna be a long teaching week. A piece of blood, apparently, a drop of blood, and then you add antibodies to it. If you see this immune response, it's because the antibody you added recognized the antigen on your red blood cell. So let's learn what an antigen is and what kinds of antigens do we find on red blood cells. And then why do we care clinically? Everything I do in this class has a clinical spin to it. Everything. You need to take this with you forward. So clearly blood typing is important because we have people donating blood all the time and people need blood transfusions. But there's more to it than just that. We also worry about blood types and incompatibilities between mom and the fetus that she's carrying. And this is a very likely scenario. The blood type that mom has is most certainly, like it's a good statistical finding that it will be different than what the fetus is. And what will happen if there is this incompatibility? Can the mom's immune system go on the attack and destroy the fetus? And what part of it will it destroy? And it's the fetal red blood cells. This is called hemolytic disease of the newborn. And I will teach you how we can identify it, prevent it, and if we can't prevent it, how do we treat it, and who do we treat? And there are examples of how I will test on this on your lab exam in the lab manual under the experiment where you're going to be blood typing my blood. So if you want practice test questions, they are already in your lab manual. So what is an antigen? An antigen is anything that can provoke an immune response. That's what an antigen is. Some antigens are better at provoking an immune response. Some can provoke an immune response within seconds. And this can lead to a very serious condition called shock. You've heard of shock, right? Anaphylactic shock. And you will learn about all the kinds of shock in Unit 3. But we've heard and we hear all the time about peanut allergies, right? Well, that's okay. So the peanut has an antigen. And when the person ingests or even comes into contact with peanut oil, that antigen is around and it provokes an immune response. And the person can die. When this happens, this very severe immune response, what happens is that we have basophils. Basophils mature into mast cells. And mast cells will release copious amounts of histamine. And when histamine is released in great quantity in your body, thanks to your mast cells, it causes all of your blood vessels to vasodilate. And this means you no longer have adequate blood pressure on the blood inside. You cannot move your blood. And if you do not get blood delivered to your brain, you lose consciousness and your brain centers start to die that regulate things like breathing, heart rate. This is a very serious condition. So an antigen is anything that can provoke an immune response. Some are better at it than others. Some are really bad at it, and it might be a delayed response where the person might not know they're having an allergic reaction to something until days after they've been exposed to this antigen, and then the diagnostic nightmare begins of trying to backtrack as to what they might have been exposed to. Have you heard of poison ivy? Right? That's a delayed immune response. It might be 24 hours to 48 hours before you actually appear with that horrendous rash. And by the time it presents itself, you probably have touched the area and spread it to other parts that weren't initially exposed to that antigen. That happened recently to my father-in-law. And let's just say he touched other parts that he probably wished he had not touched prior to knowing that he had poison. It was actually poison oak where he lives, poison oak. So an antigen can provoke an immediate response or delayed. This means that we can turn it into a descriptor word. We can say it's antigenicity. Some antigens have more powerful antigenicity than others, and that means they can provoke an immune response that's very quick. When we are giving blood transfusions, we are giving mass quantity of cells that came from a different person to a recipient. And that means we most certainly need to know what antigens are on the donor's red blood cells, because they can provoke a very powerful antigen response, right? An immune response. Very, very intense antigenicity. Now, what will respond to an antigen? Antibodies. Antibodies have lots of functions in your body. If you took micro, you know that they don't just fight off illness, right? They have many other things they can do. One is to neutralize antigens, and we'll talk about what that means. Where do they come from? They come from B cells, one of the two major flavors of lymphocytes. B cells come from the hemocytoblast, that multipotent stem cell that I told you about in lecture today. Hemocytoblast cells are found in your red bone marrow. If you are under 20, then you still have a lot of red bone marrow in your appendicular skeleton, the long bones of your arms and legs. If you are over age 20, well, it's all downhill after age 20 in life. Your blood synthesis is occurring still in bones, but of your axial skeleton, like your sternum, your vertebrae. So in this red marrow, you have a cell that replicates and divides, and one of the cells it can generate is a B cell. When B cells are finished maturing, they generate antibodies. B cells can only generate one type of antibody that will recognize one antigen. So what's your name? Nicole. Okay. So clearly, Nicole is an organism, and she has lots of features to her. An antibody can recognize an antigen. That means anything that can provoke an immune response. Pretend I am a B cell making antibodies. And it turns out that I cannot stand beautiful, long, brown/blondish hair. Cannot stand it. I cannot handle it. So even though Nicole has many features to her, the part that I react to, the part of her that is antigenic to me, is her beautiful hair. And a B cell, when it makes its antibodies, the antibodies can only recognize that part of the antigen. So if she is an antigen, there are different parts to her, not her arms, not her legs that I react with. I react only with her hair. And in micro, you might have learned that the part of an antigen that the antibody reacts to has a fancy name called an epitope, right? Okay, so her hair is the epitope that I respond to. It's the part of the antigen that I respond to. It's kind of weird. She's going to go home tonight and say, my teacher played with my hair during lab. Well, Cole might say, well, I react to knit sweaters that have holes in the knit pattern. So then Cole, if he were an antibody, he would react to this part of the antigen. Right? And then somebody else might say, well, I react to anything that has this kind of burgundy, maroon-ish color. And there would be a lot of you that would be singled out and attacked for that color that you're wearing today. Okay? So if I'm an antibody, that's it. This is the only thing I can recognize. Not her sweater, not the ring she's wearing. This is the only part I recognize. If there's another part of the antigen, then it's a different antibody that will react to it. Cole says, I react to knit sweaters. Then this is where he would react. He would find here, okay? He would try and cover it up. That's what your immune system does. Now, when an antibody attacks or recognizes the antigen in your red blood cell, then all the red blood cells will precipitate out of solution. And that's what you saw on the first slide, on the blue colored slide. You saw the clumping, and you didn't need a microscope to see that. It was such a profound immune response that all those red blood cells fell out of solution and formed clumps in front of your very eyes. So clearly, the antigens on red blood cells have the power to be very antigenic. And we would not want that kind of response in a patient who needs a blood transfusion. If that happened in a patient, that would not be compatible with life. So we don't want that to happen in vivo. Do you all know what that means, in vivo? In the person, like in the cells or reacting with cells. Here on the screen, you're seeing green antibodies, and you are seeing a bacterium with many different antigens on the cell membrane, just like Nicole has many antigens on her. She's got sneakers, she's got a knit sweater, she's got a striped shirt, she's wearing a smartwatch. There are a lot of features on her that I could attack and say, that bothers me. Her brown, long, beautiful hair is just one that I've picked on. And you're seeing on this screen that the bacterium has many features, antigens, and you're seeing up here 2 different antibodies that can only react with one of those antigens. Antibody A can only recognize orange triangles, apparently. Antibody B can only recognize cream or peach-colored half circles. Well, what antigens do you have on red blood cells? Your red blood cells are not bacterial cells, obviously. Your red blood cells are cells that have a biconcave shape to them. And up here on the screen, I'm showing you the antigens using geometrical figures just like the bacterial cell did. If you are blood type A, you have one of these antigens on your cell membrane. Say, the yellow triangle. If you're blood type B, you might have the yellow circles. If you're AB, you would have both. If you're blood type O, you don't have either of these antigens. Well, it's clearly not geometrical figures on our red blood cells. It's something else. It is actually a sugar at the end of a sugar chain. So up on the screen, you're seeing red blood cells. Here's their cell membrane, a phospholipid bilayer. And attached to the phosphate heads, you're seeing a chain of sugars. And towards the end of the chain, can you see how the chain has a branch off of it? And after that branch, you have exactly one more sugar after that. This is called the N, capital N, terminal sugar. And it turns out it is this last sugar that you have that determines your blood type. If you are blood type A, the last sugar you have is N-acetylgalactosamine. That's your sugar. If you are blood type B, your last sugar is galactose. If you're blood type AB, then you have chains of sugars where one would have N-acetylgalactosamine and the other chains would have galactose. You would have both. And if you are blood type O, you don't have a last sugar after the branch occurs. So, how many of you are blood type A? You have N-acetylgalactosamine. Blood type B people, you have galactose. Where are my AB people? Yeah, that's pretty rare. No ABs? You would have both. Who's blood type O? Very common. You don't have an N-terminal sugar. You lack one. Is that cool? Now these sugars are not the only antigenic part of a red blood cell. Just like in this bacterial picture, there were many antigens that were shown. Triangles, half circles, squares. So these sugar groups that I just taught you on red blood cells, this is just one kind of antigen, this sugar group. There are others, many others, but some we are more clinically worried about than these others. The sugar groups, very clinically important to us. We're not just going to say, hey, you can donate your blood to me. I'm going to find out to make sure his blood is compatible. If it's not, my immune system will attack his red blood cells. My immune system will deem them as foreign, just like a bacterial cell is foreign, and my immune system should attack that. When we give blood transfusions, we are worried about compatibility. There's a reason why the person needs a blood transfusion in the first damn place. You don't want them attacking the donor's cells and destroying them, or having that immune response that I showed you on the first slide. You're going to make things worse for that patient, not better, if you get the blood typing wrong. Now, some of you are saying, well, I don't need to worry about this because blood typing, that's all very automatic these days. In a clinical setting, someone's going to I will see the patient's blood type on their chart. I don't really need to worry about this. Yeah, you do. Yes, you do. We are always in training for the zombie apocalypse in this class, remember? And if Carl gets shot and needs a person-to-person blood transfusion from his father, Rick, we need to be worried about this blood typing. We give person-to-person blood transfusions a lot. It's not ideal. It's not what we want to do, but we do this a lot in the field, in military battlefields, when someone's injured and we're buying them precious moments because we've got another soldier who is compatible and can give a direct line of blood to that injured soldier. So this whole hospital setting being controlled, that's cute, that's darling. And those are our ideal conditions. But the fact is, life unexpected is to be expected. Did you learn nothing about my story this morning? Right? So there are other antigens we need to worry about. What's another one that we're worried about? Rh factor. What is it? Why is it called Rh? It was first identified as an antigen in rhesus monkey red blood cells. rhesus monkeys. That's spelled R-H-E-S-U-S, and that's why we call it RH factor, the RH from the rhesus monkeys. Now, again, these sugar groups and this RH factor, these are just two of many antigens that we see on red blood cells. But these sugar groups and this RH factor, these are the ones that are clinically important to us. These are the ones that we come across and have to deal with on an hourly basis. Now, RH factor is not a sugar. RH factor is a protein, not a sugar. And this protein is very serpentine. It threads itself through the phospholipid bilayer many times. If you have this RH factor, we say you are positive. Because it takes too long, Nicholas, for me to say, oh, you have this serpentine protein in your red blood cell membrane that we first identified in rhesus monkeys, so you are RH positive. That takes too long. We just say positive. If you don't have RH factor, then we say negative. So if you are O negative, you don't have a sugar N-terminal group, and you don't have the RH factor. That's what that blood type means. If you are O positive, you don't have the N-terminal sugar, but you do have this RH factor. And if you took Bio 20 as a prereq for anatomy, then you learned that there are genetics associated with blood typing. Now, if you're smart and you remember your genetics and you love your genetics, then you would know sugars are not coded for by a gene. Genes do not code for a sugar. Genes lead to proteins. That was part of your gene expression lecture. So how did your teacher pull that over you in Bio 20 and make you learn about the genetics of blood typing if sugars are not coded for by genes? How can we even study the genetics of blood types? Oh, well, see, here's the cool part that most people don't know, even if they've taken a genetics class. An enzyme puts that sugar. An enzyme makes these sugars link together. So we can study the genetics of blood typing when we start thinking about the enzyme that is coded for that will put a particular sugar on. The enzyme that puts on N-acetylgalactosamine is a totally different protein than the enzyme that will put on galactose. So we can study the genetics of blood typing. And the RH factor, well, that's even easier. That is a protein, and clearly that is coded for by a gene. So we can study the genetics for both ABO blood types as well as RH factor. So what does that look like when we're talking about the genetics of blood types? How many of you took Bio 20 or a genetics course? And you remember, I love me a Punnett square. Don't know? No? I love me a good 16 or more Punnett square. Oh, those are good. That just makes, well, I was going to say that makes my nipples hard, but oh, I love me a Punnett square.
Read that before bed. It's like Sudoku.
You like your Punnett squares, right? I love Punnett squares. They are awesome. So I'm going to teach you the genetics of blood typing, and I have to tell you that we're going to play Who's the Daddy? We're going to play that. And there are practice problems in your lab manual that go along with that theme. You know, there's been a baby misplaced in the hospital. That still happens these days. You know, is it Bob and Mary's baby? Or is it Nancy and Phil's baby? You know, whose baby is it? We're going to play that. And I have to tell you that one time I had a student, after I taught the genetics of blood typing, where she said, I don't think you taught it right, Kara. You didn't teach it right. And I said, I'm certain I taught it right. In fact, I'm going to teach genetics this summer. I've been trained as a geneticist. I got my genetics down. She said, no, you clearly, after all the practice problems we've done, both my parents are blood type O. I went, yeah, okay, good. She said, I'm blood type B. And I said, and the class got real quiet. And I said, well, are you sure you weren't adopted? She's like, I'm sure. I have pictures in my baby book of my mom being pregnant with me. And I was like, okay. Yeah. So here's the thing. It was so upsetting to her. So very upsetting to her. And she had just lost her dad. The person she knows as dad. And I ran into her semesters after she took the class. She was sitting over by the BGS building, and I came up and was like, how are you doing? So good to see you. She says, you know what, ever since that class, I can't get past the blood types. And I said, look, we need to have a talk. She said, my dad, I had just lost him. I said, I remember, he had cancer. He had brain cancer. But you see, it was not the outbreak. The cancer had come back. It was not the only time he had the brain cancer. It had already metastasized, and it came back. He died from that metastasis. So I said, think about this logically. Did your dad have the history of cancer prior to your parents trying to conceive? Yes, she said. I said, I would bet money that your parents, faced with your dad's poor prognosis at the time, wanted a child to carry on the legacy. I would bet money that when your dad was going through chemo, he was not a good sperm donor, or should not have been. I would bet money that your parents probably had a sperm donor. Not that your mom had an affair on your dad, but there's probably another side to the story. And when I said that, she looked at me and she said, it's funny that people in our family say I look so much like my uncle, my dad's brother. I said, why don't you ask your uncle what blood type he is? Blood type B. So we talked again, and I said, don't you think it is a very plausible scenario that your father's brother gave this amazing gift? Your parents had you, and it wasn't anything bad. It was a beautiful thing. Don't you think that's a possibility? And she said, yes, it's a possibility. I just really want to ask my mom about this. And I said, you can, but you can't take that question back. When you put it out there, you can't take that back. What do you know to be real? This person you know is your dad that you lost. He's been with you since you were born. You have pictures of him at the hospital with your mom. For all intents and purposes, he is your daddy. What good will it do if you just corner your mom and say, was Uncle so-and-so really the sperm donor? What good? What will it do? Except maybe provoke some anxiety and sadness in your mom, potentially, and you both lost someone. What good will it be? I could not make that decision for her. I just said, you can't take that question back when you ask it. What will it give you at the end of the day? And to this day, I don't know if she ever asked her mom. I just left her with a scenario. So if you find out you are a certain blood type and you ask your parents about their blood type, and now you know the genetics that I'm going to teach you, proceed with trepidation. Proceed with trepidation before you start saying, Mom, and if you're going to have that conversation, probably don't do it in front of Dad, okay? So here are two homologous chromosomes. Let's say it's chromosome 6. Let's just put it out there. So here's the chromosome you inherit from mom and a chromosome you inherit from your supposed father. They each contain a gene that will code for an enzyme to put on one of those sugars I told you about. The thing is, with blood types, the ABO blood types, we do not have your typical Mendelian genetics. In Mendelian genetics, you learned about dominant and recessive, and you learned about these traits, these genes leading to characters. And the dominant gene is the one that is, quote, expressed. The recessive one is the one that's, quote, silenced. And you do not, quote, see it as the phenotype, the character in the organism, right, if it's recessive. But with these enzymes, they are codominant. Both are expressed. And that is the reason why this person, you can see their genotype. They have the enzyme that will put on N-acetylgalactosamine. They also have on the other chromosome the enzyme that will put on galactose. And that means the phenotype we will see in this person that they are blood type AB. Both alleles are expressed. Both are used. And that makes for messier genetics. So the genotypes, right? In typical Punnett squares, don't we use capital letters for the dominant? We use lowercase letters for recessive. Well, the letters we use for blood typing are different. We use a capital I or a lowercase I. And along with the I letter, we have another letter, A or B. And these are superscripted. So this person's genotype would be capital I superscript A, capital I superscript B. That would be the genotype. Well, let's make a list of the genotypes. The alleles. The allele for blood type A, capital I superscript A. The allele for blood type B, capital I superscript B. And if you have a little I, that means one of your alleles does not code for the enzyme, does not code for an enzyme. And if you don't code for an enzyme, then you can't put on the sugar. So if one of your alleles that you inherit cannot code for a functional enzyme, we give you the genotype of little I. We know that there are many different blood types thanks to these genotypes. Blood type O is one of the more common blood type in our population. If you go to other places in the world, the frequency of these blood types would be different frequency in different ethnicities as well. If you're a blood type AB, that's why I said earlier, oh, no ABs in here, that didn't shock me. That's a pretty rare blood type to see. Most of you in this room will be blood type O, but not all. If you're blood type A, your genotype can be either that you're homozygous or heterozygous. All you need is one functional working gene to code for an enzyme to put on N-acetylgalactosamine, and you have that A sugar. If you're blood type B, you can be homozygous or heterozygous. If you are blood type AB, as shown in my previous example with the 2 homologous chromosomes, this is your genotype. Superscript A, superscript B, both are expressed. If you're blood type O, this is your genotype, 2 lowercase i's. And over here, continuing with the theme of the geometrical shapes, I'm showing you the same shapes as you've seen in an earlier slide. But now you know it's not geometrical shapes that determine your blood group, but rather the sugar. And it's an enzyme that determines what sugar is put on, if any, at the end of the chain. So far, so good? So let's play. Who is the daddy? Or which baby is Bob and Mary's? So you make your Punnett square. Now, if you're a real, true Punnett square connoisseur, then you know which parent goes at the top of your Punnett square, and you know which parent goes on the side of your Punnett square. I don't care. I don't care if you know which one is supposed to go where. Just make your Punnett square. So Mary, you're told, is blood type O. Well, then what's her genotype? Little I, right? So let's put Mary at the top of our Punnett square. When she makes her oocytes, she really only has one allele she can give, really, one type, and that's the little I variety. Bob, you're told, is blood type AB, so what's his genotype? In 50% of his sperm, he's going to give off the superscript A allele. In 50% of his sperm, he will have the superscripted B allele. Punnett squares, you just cross multiply. So what blood types could their babies have? They will either be blood type A or blood type B. So which baby is likely theirs? Baby X or baby Y? They can't have, if Bob is really the daddy, and we're going to assume he really was the sperm donor, they cannot have a baby that's blood type O. Does everyone see that? It's either blood type A or B. So baby Y is most likely theirs. Of course, before we send the baby home with these two, we will do other genetic tests to more firmly conclude that baby Y is theirs. Now, you heard me talk about Rh factor. Rh factor is also called Rho-D, R-H-O-D. Sometimes people refer to it as just factor D. So be ready for all of these ways of describing the Rh factor. And the Rh factor is coded by a class of genes, a family of genes. And that makes the genetics of this type of antigen a little bit messier. And there are other antigens that can go along with this, like the RHC and E family. Let's just focus on the RHD family because that is the most common. And the RHD family is going to create this Rh factor that I showed you on a previous slide, that very serpentine protein that goes through the red blood cell membrane. And if we only focus on that one for the Rh family, if you are homozygous dominant, you will have the Rh factor. This one does follow classic Mendelian genetics. If you are heterozygous, you will still have the Rh factor. If you are homozygous recessive, then you are negative. You do not have that Rh factor. How many of you in here are Rh negative? Okay, so I have one male, at least that we know of, right? That is Rh negative, and I have two females that are Rh negative. Ladies, you're going to want to pay attention when I get to hemolytic disease in the newborn, because you have some shots coming your way should you choose to become pregnant. Statistically speaking, most of us in the room are Rh positive. Statistically speaking, you are more likely to conceive a child with a partner that is Rh positive. And statistically speaking, I will show you the genetics, that means the fetus you may carry one day will be Rh positive. That means the fetus you carry will have a blood type that is not compatible with yours. And that means for 36 weeks, your immune system could go on the prowl and attack the very fetus you're supposed to nurture and allow development for and birth. And then that fetus has been attacked for most of your pregnancy by your own immune system. How do we prevent that from happening? Because ideally, we want all moms to go home with their take-home package, right? We want them to go home with their little parasite, and that parasite we want to be as healthy as possible. So I'm going to tell you about the shots, plural, you might end up getting, or you should end up getting. And I'm going to tell you why you want them. Even if you're afraid of needles, I don't like, needles hurt. I don't like them either. But these shots that we get, immunizations that we get, we're better for it. Do you understand that's a recent thing? Getting immunizations is a recent thing. Like within the last 150 years recent. That sounds like a long time, but it's not. Immunization, if you asked people from 100 to, let's go back 200 years ago, if you said to one of our ancestors 200 years ago, I'm not going to immunize my kids, that ancestor might bitch slap you. And that ancestor might say, do you know how many kids I lost? And now you're telling me, person from the future, we have these magical things called immunizations where my kids could have lived and not died from smallpox. You're telling me we have things where they would never get, do you know how many kids I saw get so sick and die, my own children? And you're telling me it's a shot and it's preventable and you're choosing not to? Do you know our ancestors would probably, they would want to hurt you. They really would. They would. I don't like needles either, but the benefits of these immunizations, the shots that you're going to be getting is like an immunization. And it will prevent your immune system from attacking your fetus. Yeah.
So if your immune system attacks the fetus, is that what leads to a miscarriage?
It can. If you're, see, remember the antigenicity part? We need to talk about that. If your immune system is already like acutely aware that that parasite you're carrying, I call it a parasite for a reason, right? It's not you, it's a foreign thing living off of you. If your body figures out that that is a foreign thing and deems it a threat severely enough, you will cause that fetus to be spontaneously aborted. And if I can prevent that by giving you a shot or two, I think I should. And I think you should sign up for that. Yes.
Doesn't that normally happen with like the second child?
So that is why we have to talk about this antigenicity thing. Remember delayed response? And you're hearing someone say, isn't that a second child or after, second, third, fourth child? Okay, we're going to talk about that. How do you know with confidence that these two ladies have not been pregnant before? Ladies, have you been pregnant before? Not that they're fessing up to, not publicly. How do you know? People lie all the time on their medical documents, all the time. And fact, women who have lost a baby through a spontaneous abortion, or women who have lost a baby through elective abortion, don't like to talk about it. It is a significant loss. Whether it be a choice they made or not, it is a significant loss. And most women do not acknowledge that the pregnancy happened. That invites a whole conundrum when you're trying to prevent in a woman who now says, I really want this baby, and now you're trying to prevent their immune system from attacking the baby. They might say, oh, this is my first pregnancy. You need to treat them as if it's their 13th pregnancy. You don't know for sure if it's their first, second, or 13th. You're going to conduct yourself in the best way possible as a healthcare provider to ensure that both mom and baby leave that hospital in the healthiest way possible. Agreed? Okay, so we're going to talk about this first versus second pregnancy issue. That all goes back to the antigenicity that I told you about. Is it going to be a delayed response? How long of a delayed response can it be? Months, years worth of delayed response. Either way, if we're talking about a mother's immune system attacking her fetus, this is no bueno if she wants a baby. You had a question. You had your hand up. Yeah, so you're thinking about the delayed response. We have to address that. Okay, so it takes too long for me to say antigens on your red blood cells versus antigens on your skin cells versus antigens on your neurons. It takes too long for me to say that sentence. So if I say agglutinogen, that one word simply says I'm talking about a red blood cell and the sugar you have on it or the RH factor you have. If I say agglutinogen, I am talking about red blood cells and the antigen they have. If you are blood type A, your agglutinogen is N-acetylgalactosamine. If you are blood type B, your agglutinogen is galactose. If you are A positive, your agglutinogen is N-acetylgalactosamine and RH factor. If you are blood type O, you don't have a sugar agglutinogen. And if you're O negative, you also lack the RH agglutinogen. It takes too long for me to talk about antibodies that will attack red blood cell antigens. You have a lot of antibodies in your body. If I say agglutinin, that immediately means I'm talking about antibodies that will recognize red blood cell antigens. It's one word and it describes all that. So you will read these words on a lab exam. Make sure you know what an agglutinogen is versus agglutinin. Blood type A would have the agglutinogen and acetylgalactosamine. All right, where are my blood type A people in here? All right, you have N-acetylgalactosamine as your agglutinogen. What agglutinins should you have? These agglutinins, these antibodies, are floating in your plasma. Should you have antibodies that attack your own antigens? You see, when you express these antigens, we call them self-antigens. You should not create antibodies against self. If you do, what do we call that? An autoimmune disorder. So if you are blood type A, what antibodies should you make against foreign blood types? You should make agglutinins that are anti-B. right? You are blood type A. Your body should protect you against all other blood types. So if you have blood type A, you have anti-B antibodies. If you are A negative, you would also have anti-RH antibodies. Your body makes antibodies against antigens you don't have. That is weird to think about, really. When do you start making antibodies? We think of newborns, we say they're immature. We say their immune system is immature. Actually, babies do have some antibodies that start appearing before birth, and even it spikes shortly after birth. You have a question? Okay, so here's the thing. True. Babies' immune systems are immature because we say they haven't been exposed to all of the bacteria. Let's just take bacteria, right? They haven't been exposed to all these bacteria. Children who go to daycare at a very early age get exposed to a lot of germs. They get sick very frequently. But once they're around age 4, they've been exposed to a lot of germs. Their immune system is pretty solid. They're just sick little people during those first 4 years. That's why it's so hard for kids who go to daycare in those early years, because they get sick so often. They're exposed to everything. My kids never went to daycare. Lucky that I have a spouse who believes, no, we take care of them. Having a teaching job means we can flip our schedules. If I was home during the day, Honey was teaching during the day, and when he came home, I would teach night classes. Our kids didn't have to go to daycare. We were lucky in that regard. My kid now goes to college and lives in a dorm. He's living in a cesspool of germs. He has not been healthy for more than 2 weeks since he's been there. He hasn't. He's been sick chronically, over and over again. And I was like, oh, you never went to daycare, so suck it up. You're gonna. Mono has gone through his dorm. He's already had that, so he was like, I'm good with that one. I've had mono in high school, so he was fine. But all of his floor mates wiped out with mono. Not dead, but just wiped out.
The Walking Dead has begun.
Yeah, it really has. So you make antibodies against foreign antigens. You would not want to make antibodies against your self-antigens. You would then attack your own tissues, your own cells, and this is not okay. What agglutinins would a person have? My blood type B people, what agglutinins would you have? Anti-A. If you're blood type AB, what agglutinins would you have? You would not make anti-A. You would not make anti-B. If you're blood type O, what agglutinins would you make? You would make both anti-A and anti-B. And some people are sitting here going, wait, I'm fairly certain you should have described another agglutinin. What about anti-O antibodies? No such thing. You can't make an antibody against nothing. When your B cells start making antibodies, it's because an antigen has been presented to them by an antigen presenting cell saying, see this? Here, boy, go get it, go kill it. You can't, your antigen presenting cells can't take a negative space. They can't, if there's no N-terminal sugar, what do they present? There's nothing there. You can't make anti-O antibodies. There's no sugar to make an antigen to, or an antibody to that antigen. There is no sugar. Does that make sense? You had to put your hand up again? No? I'm just now hallucinating it because I need to eat. All right, so let's talk about this immune response that you saw in the first slide. You're going to figure out what blood type I am. And for some of you in this room, you already know what blood type I am because you had me for another class, say anatomy, and I taught you about blood typing, and I even went to the physiology lab and said, here's my blood. When you saw my student draw my blood, remember this is what they were using it for. So here's last semester's blood from me. So you're going to take my blood, and you're going to take I'm going to give you droplets. 3 drops, and you're going to put those, I'm going to put those 3 drops on a slide. This is next week. 3 drops of blood. To those 3 drops of blood, you're going to add antibodies. You're going to add agglutinins. Anti-A antibody comes prepackaged in a blue solution. That's why you saw the blue on the screen. When this antibody was added to a drop of blood, it colored the blood blue. That's why you see the blue splotch on the screen. Anti-B antibody, you're seeing the yellow, comes in a yellow solution. See? And anti-RH antibody comes packaged as a clear solution. So to these 3 drops of blood, to the first drop, you're going to add anti-A. You're going to take a toothpick and you're going to mix. If I have the A antigen, that anti-A antibody is going to lock onto it, just like Nicole. Nicole's beautiful brown hair, I locked onto it. Don't you love it when people play with your hair, by the way? No? Even if she was lying, she's like, just get away from me, it's weird. Here's the anti-A antibody, and if the A antigen is there, the antibodies are going to lock onto it, creating these clusters, and then they precipitate out of solution, and this is what you will see. If you see this immune reaction occur, it's because both items are now present. I provided the blood with the antigen A. You added the anti-A antibody. They reacted with each other, and now my red blood cells precipitate out of solution. If you saw that clumping, that's what it's called, clumping, then you would say, Kara, you have blood type A. Well, what if you added anti-B? If you see the same kind of clumping, you would say, oh, you're blood type AB. If you don't see the clumping, then you would say, oh, you're just blood type A, that's it. Okay? In order to see this, 2 things have to be present. One, you the nurse or future healthcare, you are adding the antibody from your stock solution. Your patient is providing the antigen. If these 2 things now unite, you will see clumping. It is also called agglutination. Agglutination is not coagulation. Agglutination is an immune response between an antibody and its antigen. Coagulation has nothing to do with the immune system. Nothing to do with B cells. Clotting, coagulation deals with platelets. That's a totally different formed element in your blood. So this is agglutination, not coagulation. I beg you to know the difference. If you add anti-A and you don't see see I have clotting on the brain, and you don't see agglutination, clumping, and you add anti-B and you still don't see agglutination, clumping, then I would be blood type O. So you're going to figure out what blood type I have next week. And it is an awesome blood type. You want it. You definitely want me to be your blood donor. And right away, some of you who understand blood typing, you're already making a guess as to what blood type I am. And you're wrong. It's my little joke, and you won't know the punchline until next week. It is a pretty awesome blood type, though. It is important that we recognize that there are antibodies in our plasma, but when we blood type someone, we're adding antibodies to their blood. Little drops on a slide. We even do it on a card at a mobile unit. So before you gave blood or attempted to give blood, they blood typed you. You know what blood type you are, right? And they gave you a little card that said, don't come back ever.
Never ever.
Were you actually able to fill your bag?
No. So when
They can't use it if you don't fill it appropriately.
No, I didn't even get to that point. Like, I was already anxious for it. I prepared myself and waited. I got 2 interns that were doing it, so the process was getting elongated. And so she pricked my finger. She didn't do it hard enough. So then she had to, like, squeeze it out, and then that's where
You started meltdown.
Yep, I passed out. And so it was for extra credit for anatomy. And I was like, can I please still give blood after I passed out and I was laying there? She's like, honey, no.
Nope, they won't do it.
So, yes.
Because your blood pressure at that point was low,
Yeah.
and you would not have filled the bag anyway. I fainted halfway through, was not able to fill the bag, and they discard it. It's not, they can't use it if it's not full. So,
There's a trick for that.
huh?
I was told there's a trick for that. You like flex your calves, hamstrings, glutes, and then you give your blood. Because like the blood drop, blood pressure is where all the blood's going from your head to your legs.
So,
So you flex all of it, it just kind of stops.
they, trust me, when you're a blood donor, they will do every trick to keep you going if they already have you hooked, if they're already mainlining you. So my pallor, the color of my skin, while I was donating blood, got real ashy real quickly, and they caught it. So they tilted my bed so that I was head down, so that my blood was draining from those extremities. Didn't work. They tried then to put ice around my neck so that I wouldn't faint, that my blood pressure didn't work. And here's why it didn't work. Because when they inserted this needle the size of Excalibur into your arm, they of course put it in a vein. That's different from doing an arterial blood draw. We don't do arterial blood draws when we donate blood. They go through the vein. Arterial blood draws are very painful. They are done in a different place. They don't go to the antecubital fossa. They go down here to the radial artery. We'll talk about those later. So they do a venous puncture. You have valves in your veins. The needle was inserted, and then they tape it in place because you're going to be there a while. And the whole squeeze, this little cushion thing to pump the blood, don't tell me to do that. Don't tell me to make a fist when you're drawing. I will start to faint. That's all the privilege. I know what's coming. Don't. So when Farouk comes to draw my blood, and you will see him probably draw my blood, he knows not to do that to me. There's a reason why I have him. I don't go to the health center because I fainted on them, and they told me not to come back. These are nurses that told me not to come back. I know. The irony is not lost on me.
Oh, jeez.
So Farouk, most of the time he shows up, when he draws my blood, he will bring pastries to reward me. you all benefit from that when he does that. I bring him healthy stuff from my garden to pay him for his time. But he knows not to use these big needles. He uses a butterfly on me. It's smaller. I do better. He doesn't have me do this. He distracts me. He'll say, so how are the boys? And he's distracting me while he's putting on the little rubber thing, and I'll say, stop it, Farouk, I know what you're doing. I will need at least 2 of you on either side of me to hold my head in case I do faint. And he will tell you all to put your phones away, because some of you are like, this is hilarious. Let's videotape Kara having a meltdown. And he'll say, she's your first patient, you need to take care of her, not videotape her. And he'll distract me, and he will draw my blood enough for all of the phys sections. And then afterwards, I will be a complete mess, and you will have to do your blood lab while I recuperate, which will take me all day long. And he won't leave until he knows I can actually stand up and talk right, because I will feel faint. And you'll think I'm drunk. I won't be. He knows I just don't do well. So when you go and you give blood, they use a bigger needle. They'll tape it in place because you're going to be there a while. You're supposed to play with this little cat toy, trying to push the blood into the bag that you're trying to fill. This person inserted the needle right by a valve. So it was painful while it was there, which, I mean, it wasn't that painful. I can get through it. But what was weird was that I could feel the valve fluttering as the blood was trying to go through the vein. So it felt like I had a bee kind of fluttering around in my vein. That's how, and I swear there was a sound that I was hearing. It was like, it was weird. And so that's what made me spiral down the fainting well. Yeah.
Because actually I was drawing blood on someone, and I was in a valve too, and I could hear the fluttering, and so I kind of just withdrew it back.
Pull it back out. Yeah, it was, by the time they saw me and they checked on me, I was like, it feels like I have it feels fluttered, and they were like, oh, we have it by a valve. So the person then said, I'll just move the needle around a bit. Didn't help. That did not help. It was like, I'm going down. I'm going. Bye. And that's when I fainted. I woke up with all this ice pack around my head and blankets on me and my bed thing tilted. And that's when, just like the nurses here, they said, don't come back. Volunteer in other ways. Cole, you had your hand up. You forgot your question.
No, I didn't have a question.
I thought your hand was up. See, I'm hallucinating again. I thought I saw your hand.
Was it up like this?
Yes. No? Seeing things. I swear your hand was up.
At what point was it up?
Earlier. Not now, clearly. It was. Maybe you stretched. I
had a question way earlier about with like the peanut thing. That like some people like they get the allergic reaction when they're eating it, and others don't even have to touch it. It can just be like in like close proximity.
They can, if you ate a peanut and then they can touch the same table with the oils and then contract an allergy from that, or have an anaphylactic shock from that. Yeah, serious stuff. That's a very antigenic antigen. Okay, now I have a question.
Okay, so back on that actually, because I was going to ask earlier. So what do people with those allergies like lack that they can't tolerate that?
So we're not really sure why some people develop an allergy to something and others don't. We call these allergies sensitivities, and there are 4 classes of sensitivities, numbered 1, 2, 3, and 4. If you want to learn about them and have to know them, take patho, because that's where I have more time to talk about these 4 classes. And we also identify them as A, B, C, D, where A stands for it's a true allergy. We're not really sure why people develop allergies, not sure. B stands for B cell response, specifically. C stands for cell-mediated, and D stands for delayed. So anyway, your typical peanut allergy is a type A, or type 1 sensitivity. Not sure why some people develop allergies to certain things and others don't. We do know, however, that you start making antibodies at a very young age. If we're talking about the B, anti-B and anti-A antibodies, they start before, around, slightly after birth. And here's why. You think of a newborn not having a strong immune response because they haven't been exposed to things, right? They don't know, their young body doesn't know what's foreign. But here's how your immune system works. If your immune system worked by only developing antibodies, once you've been exposed to them, all of us would have an immature immune system by that standard. Have you been exposed to every single bacteria or virus ever in this that you could ever come across in this world? No, you haven't. So here's how your immune system works by default and then adds to your repertoire of antibodies when you do get exposed to things. So fact, answer for me, should you make antibodies against self? No. Do you have your self-antigens when you're developing in utero? Yeah, you're becoming a self. So here's what your immune system does. It's actually quite clever. How many of you know the actress Alyssa Milano? She was in a TV sitcom a long time ago called Who's the Boss? Have any of you heard of this TV show? Okay. So there was, Alyssa Milano played the daughter of Tony Danza. So this actor was her dad in the show, and he was a single dad with a kid, and he ended up being the housekeeper nanny for a single woman who had a child, a son. Danny Pintaro was the son. And as the show went along, as young kid actors do, they grow up and they're no longer cute, so the show ends. That's what happens. It's fact. This is part of the reason why we don't have the Cosby Show anymore. Never mind that he, you know. Anyway, so there was a part where Alyssa Milano was old enough to date, and her date came to the door. She was upstairs still getting ready, and her TV dad, Tony Danza, answered the door, and he said, "Come on in." And this young man comes in, and they start talking, and Tony Danza does all of the traditional dad things to a date, right? Where are you taking my daughter? When will you have her back? And he's got his responses polished. He is just, and Tony Danza, he can see it. He can figure it out, and he's giving you the facial clues like, this guy thinks I am just one, he's too slick. He's too good. This is too good. So Tony Danza ups his game, trying to figure out if this guy is very forthright. So he turns to this young man, he says, you seem like, you know what, you seem really cool. I'm so glad that my daughter's going out with you. Hey, can I get you a beer? And that's what he said. And so Tony Danza gets up and he picks the guy up by his shirt and throws him out the door. And Alyssa Milano comes down and she's like, what happened? He's, oh, he got sick. He can't take you out on a date. Said to say sorry. And I watched that and I thought, that is exactly how our immune system works. It's exactly like that. Your immune system has all of your self-antigens. When you were born, you had all of the T cells and B cells you could have. All of those T cells and B cells can only recognize one antigen, just one. You all correctly said we should not have immune cells that recognize self. because then we would have an autoimmune disorder. Your thymus, for example, is where your T cells are selected for. And your thymus works just like Tony Danza. Your thymus turns to your T cells and says, do you want this? Do you want this? And your thymus uses self-antigens. You had all of those before you were born. So your thymus is already maturing your immune system by offering T cells and your bone marrow B cells self-antigens, saying, do you want this? Do you want it? And if the T cells, like the kid, go, yeah, then your immune system, your thymus, and your bone marrow goes, and you're out of here. Kills off those T cells and B cells. You shouldn't have them. They're going to kill you. So that's how your immune system starts. Do you want this? If those T cells and B cells go, yep, that's what I'm made for, that right there, that's mine. Then your thymus and your bone marrow goes, punk, gone. And that means when you're born, you already have an arsenal of T cells and B cells by default that will recognize anything foreign you ever might come across in your life. The problem is, of course, is as we age, if we are no longer exposed to those antigens, those T cells and B cells are like, haven't been picked yet, always the bridesmaid, never the bride. And then eventually, they die off, as if your body is saying, well, if you haven't used it yet, probably you're not ever going to use it, so let's get rid of it. Declutter. And that's why our elderly are susceptible to new flu strains and things like that, because they probably have not been exposed to it prior. Does that make sense? So you're born with an arsenal of T cells and B cells. You being exposed to these foreign things means your body goes, right then, we need this one, this antibody from this B cell is so important to protect us from smartphones. We've been exposed to it, so we need this ramped. That's how immunizations work. We give you the antigen, your body goes, ah! We need this T cell and we need this B cell, and that's how you develop them, you mature them. You've been exposed to it. Now, if you ever get exposed to it out naturally, you already have those T cells and B cells selected for. They've already gone through clonal expansion. They're ready to fight the fight, and you won't get as sick from it. That's why flu shots are so important. And a lot of people think, oh, I don't get the flu shot. Is this you? Because I get the flu every time I get it. I'll call bullshit. You probably were already sick or infected with that virus before you got the shot. It was just bad timing. Or you have an egg allergy you didn't know about, and you're reacting to the flu shot, which is developed in chick embryos. That's usually the issue. But to say that the flu shot makes you get the flu, no. That would be totally unresponsible for the CDC to recommend something that makes you potentially sick and could die from it. We are having one of the worst flu seasons on record. People are dying. Young people are dying. By young, I mean my age. That's young to me. To you, it's ancient. To me, it's young. They're dying of it because they think it's just a bad cold. And by the time they go in, it has compromised their air passageways to the point where they're dying from it. Scary. All right, so we have our antibodies at a very young age. And specifically, we start creating our antibodies against blood types very early on. Why? Why? It's not like a baby is exposed to blood, or are they? Yes, they are. It's a very bloody process when they're born. And here's a game that babies love to do. Mom and Dad, here you go. Baby goes, Dad, here you go, baby. Babies are awesomely orally fixated. That's how they learn about everything. Everything goes in their mouth. That's how they learn at an early age. And if you are that parent that don't put that in your mouth, no, and you're telling you're restraining your baby's hands because it is germ. This is how they learn. You're stopping them from learning. And yet, there could be germs. You're in a fog of germs right now. You just heard me say that's how their immune system selects for the T cells and B cells. I'm not saying you want to take your baby out and expose them to a kid that has chickenpox. I'm not saying that. But they have to be exposed in order to select for these T cells and B cells. That's the basis for immunizations. So they are exposed to blood. Why? Dad or mom has been shaving, they have a nick, baby drops toy. Oh, I was like, okay, here. Now my blood is on this toy. I give it to baby thinking I have clean hair. The tables in front of you, you all have touched them. You might have put your fingers in your mouth. My blood is on these tables. There's a bit of me in you right now. And now some of you are like, weird. But you're exposed to blood early on. You add to this an infant who's breastfeeding. And those of you who have ever breastfed, you know that you're supposed to put them to the breast at least every 2 hours. Those things are not used to all that action. They will get chafed, just like your lips, right, get cracked and chafed, right? Dry lips. Those do too. They will even bleed. And you still have to feed that parasite. The law says you have to. It will be pain. You will be bleeding through your nipples, and that kid's going to be swallowing your blood. So, don't have a kid. Hire someone to breastfeed. You can even buy that stuff now. Huh? You can pump. Yes, you can. And you will, because the baby will not always be around. And believe me, when they get full, it hurts. And when you actually let down your milk, pumping or breastfeeding, it feels like you're peeing the most amazing drunk pee through your boobs. It just feels like you do this. Oh yeah. It does. Anyone here breastfeed before? Am I right?
Yes.
And you can even feel it draining from your armpit, can't you? It's like you feel the milk moving. It's just like, yeah. And you move yourself. You move the baby, you're like, drain it from the arm. You'll move and you can feel it. It is weird. And if one of your ducts gets clogged, it can get infected. You will have this hard lump in your milk duct that when it gets infected and now is red. Very, very painful. You will need antibiotics. And you are told you still must breastfeed because you have to get that clogged out. So that's another excruciating experience. Hire someone to have your baby and feed them. That's an awesome way to go if you can afford it. All right, what blood type is this person up there? A positive? Right. But none of us have molecular goggles on when you're going to see my red blood cells in front of you, you're not going to look at it under a microscope and go, okay, I know what blood type you are. You're going to have to add the antibodies to it. And then you'll figure out what I am. Let's talk about blood incompatibility between mom and baby, since we were just talking about babies. Everyone, what blood type is this person? It's written on the card. It is A positive. Can you see the clumping here and here? In my class, we say they are what they clump. If they clump when you add anti-A, they must have had the A antigen. Otherwise, that immune reaction would not have happened. You need both antigen and antibody. You provide the antibody. Your patient provides the antigen. This person is A positive because we see the agglutination or clumping when we add the anti-D antibody. So when you are ever dealing with a patient that needs a blood transfusion, speaking of incompatibility, you must first determine the person's blood type. The next thing you do is, once you know what antigens they have on their red blood cells, you must ask yourself, what antibodies do they have in their plasma? If they are A positive, they would not have anti-A antibody. They would not have anti-RH antibody, but they would have anti-B. Once you identify step 2, what antibodies your patient has, don't give them the blood that their antibodies would recognize. It's a simple set of steps. Figure out what blood type they are. Second step, you ask what antibodies would they have in their plasma. Third step, don't give them any blood type their antibodies would attack. It's simple. So, we have donor, we have recipient. You know what blood type you are? Okay. Who here does not know what blood type they are? Awesome. Okay. Pick on you since you're close. You saw my tray of antibodies that I have in the refrigerator. Let's blood type Nicholas. I'm going to go get those antibodies. I'm going to get a big syringe and needle. I'm going to suck up a whole bunch of anti-A antibodies. I'm going to inject a whole bunch of anti-A antibody into Nicholas and say, if you live, I will know what blood type you're not. Right? So who here does know your blood type? Okay, don't tell me. You already told me. Don't tell me. Suck up a whole bunch of anti-A antibody. Squirt, inject into Nicole. Do you live? She lives. I know what blood type she's not. She can't have any A antigen. So I know she's not blood type A, and she's not AB. Otherwise, the anti-A I injected would kill off her red blood cells. They not only clump, they will start popping. That's called agglutination. That's leading to hemolysis. Now, Nicole, I have a whole bunch of anti-B. Inject. Do you live? Okay, so I know she's not blood type B. So you must be blood type O. Okay, one more. Whole bunch of anti-RH. Squirt. Does she live?
Yes.
So you're O negative?
No, I'm not.
Oh, so she doesn't live, right? We don't blood type that way. That's not what we do. What do? We take the blood out of the person, then we add the antibody. We look for the immune reaction, and then we know what blood type they have. So your blood typing would look just like this. You said you're A positive. This would be you. Good? All right. The reason why we do this blood typing is to figure out who can donate to the recipient. Donor gives to recipient. What's your name?
Roman.
Roman. Roman is willing to be a blood donor. That's awesome. We know he's blood type A. Nicole needs a blood transfusion. We know she's O positive. What antibodies does Nicole make? What does her body make? Anti-A and anti-B. If I give her Roman's blood that has the A antigen, I'm completing that two parts of the equation. And Nicole's immune system will have this massive agglutination in vivo. That is not okay. That is absolutely not okay. But can Nicole donate to Roman? Okay, hold on. What antibodies would we find in Roman? Anti-B. Does she have the B sugar? She doesn't have the B sugar, right? He has the A sugar. Is she making antibodies against the A sugar? She is. Why is it said then that people who are blood type O are awesome blood donors? If she's making anti-A, how come she can give safely to Roman? Here's why. We do a very important step before we transfuse blood to a recipient. This very important step is we spin it down. All the red blood cells go to the bottom and all of the plasma stays on top. You're going to do this to my blood next week. The plasma is where Nicole's antibodies are. I remove that part. I keep her red blood cells. I resuspend them in isotonic saline solution. And now I can safely give her red blood cells that don't have any sugar antigen to him. But if I didn't spin down her blood, could she safely get to him? No. It's because we spin down the blood that all we have to worry about is the recipient's immune system going to attack the donor's blood. If we didn't spin down, I would have to worry about both of their immune systems. I would have to worry about her antibodies attacking his sugar agglutinogens. If I spin down the blood before I give you just red blood cells, I only have to worry about you attacking the donor's blood. Okay?
Like, you think you could say that more often? It's not universal donor, it's universal donor of red blood cells.
It is. If we spin. Otherwise, O negative people are no longer the universal donor. And who's the universal recipient then? AB positive. Cole, did you have your hand up or am I hallucinating
No,
again?
I did. I don't know if it was the same question though, because you're talking about the same thing. 'Cause you were talking about like the ideal situation in the hospital though, and then if it's not the ideal situation, so then the way you're describing it seems like then you just can't give blood in the field
Yes,
setting.
you can. Yes, you can. Oh no! We are trapped in this room. We've had a massive earthquake. Nicolette is injured. She has something from the ceiling has injured her. She is now bleeding. She needs a blood transfusion. The building has collapsed out there. We're waiting for emergency personnel. I say, well, I've got all these needles in here. We've got future wannabe nurses. That's good enough. Let's do this. We want to keep her alive, and Nicolette is that desperate where she's like, fine, do it. I need to figure out here who can safely donate to Nicolette. Do you know your blood type? Don't tell me. You don't know. Okay. So let's pretend I can't get to the refrigerator because the ceiling fell. I can't even blood type anyone. I need to figure out who can safely give to Nicolette, and here's what I would do. I would go get a surface, like maybe those green trays, maybe some glassware, find a glass tray, something like that. I would find something in this room that was smooth, maybe my slides in the back. I would get my little lancet. I would start asking you all, start poking your finger. Nicolette, I don't need to poke your finger because you're bleeding already. So I'm gonna take her blood and I'm gonna put a whole bunch of blood drops on my glass slide. I'm gonna now go to each person who is now, Roman, you're first. So he says, I'm okay. So he starts squeezing out a drop of his blood onto one of your drops of blood. Then I'm going to go to Nicholas, and he's going to squirt out another drop of his blood onto a different drop of your blood. Then I'm going to go to Christopher. You get the idea. I'm going to swirl it. If I see agglutination occur between Nicolette's blood and Roman's blood, you're not a good donor. I don't care who's reacting to whom. At that, I don't care. I know it's incompatible. If I get to someone that I mix with Nicolette's blood and I don't see any agglutination, that's our winner chicken dinner donor for Nicolette. If I don't see any agglutination, then I know the two blood types must be identical. If we do not have that luxury of spinning down blood, can you understand that this limits the possibility of who can be a donor to that person? It limits us. But if we spin and then give just red blood cells, right? Just red blood cells from a donor to a recipient, this opens more possibilities of who can be a safe donor to a particular recipient. So blood type A positive people, what blood types can they get? The most overlooked is the same blood type the person is. That's the most overlooked. I don't know why. So if you are blood type A, you can get A positive blood. He can also get O positive blood because we'll spin down Nicolette's antibodies and Nicole's antibodies away from the red blood cells. They can also get, Roman could also get A negative. Why could he get A negative? Would he be making an antibody against Rh factor if he's Rh positive? No. So he wouldn't be making the antibody anyway. And if I give him A negative, there's no antigen for the Rh anyway. It's like a double negative. He could also get O negative. B positive people can get B positive, B negative, O positive, O negative. AB positive people can get any blood type. If you're negative, you can only receive negative blood. You cannot receive positive blood. Why? You would be making an antibody against Rh factor, right? Don't give them anything their antibody would recognize. Now, ideally with some practice, you will understand blood typing and how to safely determine who can give and who can receive and that sort of thing. If you have to for your lab exam, you can memorize this chart. It shows you who can safely give to whom. And if you're ever my nurse walking around on the floor with this little cheat sheet in your pocket, I don't want you as my nurse. And eventually, it might be that this is an obsolete lecture that I never have to give. We already have the technology to take blood from anyone, use an enzyme to shave off, to cut away all antigens to basically make a naked red blood cell. We have that. That means anyone can give to anyone once we treat with this enzyme. The problem is it has to go through a lot of clinical trials because anytime you add something to blood, you have to prove that it is still safe to administer to a recipient. And that's where we're at right now. Yeah.
Does that mean also they can have people that were thought of? So I know you said the blood is already out, but are they trying to do they give this type of procedure where somebody that is on a
Oh, I see what you're
Shakes off
saying.
all
I
the
don't know
stuff
if they are using that.
Gives them pedal, essentially.
But most people with autoimmune disorders that we know of are not.
So, oh,
I know, that is, it's like having sex and not having an orgasm. That's what that's like.
Sneezing is the second best orgasm, right?
It is. It's through your nose. It's just, it's awesome. And then and then that thing is horrible, as you all know.
Literally anticlimactic.
Yep, you're using the word correctly. Anyway, I don't know if they're using it for that. Most people with an autoimmune disorder to their blood type would not have lived, right? So if you have an autoimmune disorder, you're making an immune response against a tissue, but it was not severe enough where you couldn't be born. But that is an interesting question. You need a break. Come back in 10 minutes and we will finish this.
oh, actually, when we went over the physio.
So I don't care if you have to memorize this, but I would prefer that you actually with time master the blood typing concept. But here's why it's important, not just for possible blood transfusions. It's also important when we talk about interactions between mom and her fetus. How many of you are going to make a life decision for a life partner, a mate for life, based on their blood type?
I mean,
Now, I said that one semester, and I had two ladies, actually, I said, who here marries based on blood type and would make that decision? I had two ladies raise their hand, and they were from the same part of the world and same, like, religious beliefs, and they both said, yeah, that is what we do. We find out blood types, and that is part of the decision. And I was like, wow. So if you think about that as being pretty extreme, go back in time before we even knew blood types. Go back in time and you can appreciate why some women, after I finish lecturing on this, might have had spontaneous abortions because their immune system attacked and killed the baby. And just through observation of this, probably cultures developed that kind of tradition saying, we have to have this, like, just picking at straws really, but they got something right in that aspect. Most of us are not going to pick someone based on their blood type. That is, I'm speaking to the ladies. Ladies, you find, okay, I'm speaking to heterosexual ladies. I have to do this these days because it used to be so safe before the 64 genders, but now, so I'm speaking to women who identify themselves as women and who would want males who identify themselves as males as partners. Isn't this crazy that I have to do this now? Kind of is. Anyway, so ladies who would want a male partner. Okay, what would you want in a male partner, ladies? Number one. Really? That is usually not number one. Let me put it to you, the criteria. Okay, looks makes the top 5. Education would be there as well. Financing, okay, right there, that's number 1. Right there. So you find someone who is handsome, educated, gainfully employed.
Not living at home with mom.
Not living at home with mom. Unless, of course, she's elderly, and then that's a sign of actually taking care of mom. Right. Because then I'd be like, yeah, that's a turn on.
Yeah.
Exactly. And then you find out they're blood type O negative. Really? That's a deal breaker for you?
ah, shit.
All this time.
Really? That's a deal breaker. Arguably, blood typing would not be a deal breaker. But for some cultures, as I found out, it is. So why is blood type potentially a problem in a pregnant woman? Because statistically speaking, if we use that example, most of us don't even know what our partner's blood type is. And we conceive their child, right? I did not know what blood type my honey was. I didn't know until I was going through his wallet one day, looking for money. I found his blood donor card. I was like, really, you're O positive? Huh. Good to know. Good to know. Sort of like knowing his social security number. You should probably know your honey's blood type. Anyway, statistically speaking, you're going to probably have a child with a different blood type than you. And that means mom's immune system can definitely go on the prowl. ABO incompatibility is quite common, but it's usually not clinically significant to us. We don't have to worry about it. Why? Time is on our side. The baby's blood antigens, agglutinogens, are not expressed. Their sugars are not attached until shortly before birth or even after birth. In fact, it's very difficult to blood type a newborn because they might not be expressing the enzyme that puts on the last sugar. So if they do not express their enzymes yet, they're going to show up as being blood type O, right? So ABO incompatibility, very common, but clinically, no big deal to us. We don't need to worry about it. Baby's not going to make these sugar antigens until shortly around birth. Mom will likely have that baby before mom's immune system even realizes, that was in us, that had different blood than we did, not going to go on the prowl. But RH factor, time is not on our side. Most of us in this room are RH positive. Why? You could be homozygous dominant or heterozygous and be RH positive. You have to be 100% recessive, meaning homozygous recessive for that D allele to be RH negative. So I'm speaking to the two ladies that raise their hand right now, not so much Cole, because you, although you could carry a fetus, I don't, yes you can, technically you could carry a fetus. You can't conceive one, but men can carry a baby. Here's why I say that. Women have carried babies that were not implanted in a uterus. It is possible for women to have an ectopic pregnancy. Have you heard of this? Where the fetus implants somewhere else besides the uterus. Most of the time, this ectopic pregnancy occurs in the uterine tube and is life-threatening, and that pregnancy must be terminated, or most certainly both mom and baby will die. It's just a matter of when, not if. But some ectopic pregnancies have occurred where the embryo, instead of going to the uterus, because the uterine tubes have cilia, the cilia have moved the embryo out through the ampulla, out through the infundibulum, and now it's in the peritoneal cavity of the woman, and it implants on intestines. Can still get nutrients, still gets oxygen. And when the woman then has this terminal pregnancy, labor can't happen. I mean, it's not going to progress. She's going to have a cesarean section. When we determine a woman has an ectopic pregnancy, if we cannot find it in the fallopian tubes, uterine tubes, we know she's pregnant based on the hormones that we test for. If we cannot see that developing embryo anywhere in her uterus or fallopian tubes, but yet the pregnancy test says she's pregnant, we know that it must be either a tumor producing the pregnancy hormones, and we can rule that out, or we know the pregnancy is ectopic and the fetus is implanted on the intestines. Most of those pregnancies nowadays are not are not allowed, are not recommended, I should say, to allow to progress. It is still life-threatening to both mom and baby because as the placenta grows, it can break through the intestinal wall and cause severe hemorrhage. Both mom and baby would likely die, but they have happened. So guys, that's why I'm saying you technically could carry a pregnancy. You could. It is a very high risk thing to do. So if a woman has an ectopic pregnancy in that regard, do you know how do we terminate it? No, if it's not even, if the pregnancy is not even in the uterine tube, because if it is in the uterine tube, we can see it. Then we can remove the whole uterine tube. That's what we do. But if it's not, if it's in her peritoneal cavity, how do we terminate the pregnancy? How do you find that? It could be anywhere. Nope. You don't find it. How do you terminate it? You treat it as if it's cancer. She gets chemotherapy. Interesting. They just blow your mind. Mm-hmm. That's how they get rid of it, because it is a high-risk pregnancy. If they allow that to continue, most doctors will advise against it. So that is what happened. Here's how I know that. My cousin had an ectopic pregnancy. They could not find it in her uterus, could not find it in her uterine tube. They knew she was pregnant. She was trying to get pregnant. And her family could not understand why they were treating her for cancer when she didn't have cancer. She had an ectopic pregnancy. Why was she getting chemotherapy? I was like, let me explain this to you. Yeah.
How did they rule out if it, because you said it could be that or a tumor, right?
Mm-hmm.
How did they rule?
So most of the time, if it's a tumor, we know where these tumors would grow. So if we're not seeing a mass somewhere, like men, for example, could have tumors producing HCG, human chorionic gonadotropin. Not a hormone that should be in your repertoire, right? But men are given pregnancy tests. And if it comes out positive, clearly with them, we know it's got to be a tumor somewhere. And there are classic places to look for this. Some tumors grow in specific places, and we know where to look. Isn't that neat? It's kind of neat. Anyway, so blood incompatibility with ABO types, not a huge problem for us clinically because time's on our side. But if it's an Rh factor that's incompatible, that we do not have time on our side. Time is against us, and here's why. The baby starts expressing the gene for the Rh factor early on in fetal development. That means if mom is Rh negative, and she, statistically speaking, is more likely to get pregnant with an Rh positive fetus, her immune system can figure out that there's something foreign and go on the prowl. When a woman is pregnant, her immune system should be notched down because the whole thing is a foreign entity, right? And that is what our immune system does. However, there are ways where mom's immune system can get acutely aware that there is something foreign and go on the attack. Anytime there is blood mixing between the mom and baby, that is a direct way for mom's immune system to go, oh, this is foreign, because now we've got blood mixing. When can this happen in a pregnancy? Well, baby's blood, it moves through the placental vessels in close proximity to the blood vessels that mom has in her uterine wall. But they should be self-contained. There should not be mixing, at least not until birth. At birth, all those blood vessels are ripped when that placenta is born, and there is a heck of a lot of blood mixing. But blood mixing can occur before this. If we talk about a previous pregnancy that was terminated, either spontaneously or electively, that's a lot of blood mixing that can occur between mom and that pregnancy. We can get an amniocentesis, where we take a large needle the size of Excalibur and put it through mom's abdominal wall to get some of the amniotic fluid. That is a bloody process. That's going to be mixing. Mom might step off the curb and have a slight placental tear, little spotting in her pregnancy. That is mixing of fetal blood and maternal blood. So it's not just when the baby's born that these opportunities for mixing can occur. They can occur at any time with any pregnancy. And that means with any pregnancy, mom's immune system can become acutely aware that there is something foreign. If we focus just on this Rh factor business, what's your name? Britton. Yeah. Okay. I think you're at the top of my roster. You have the last name that. Yeah. So you're up in the higher quartile. That's why I'm remembering you. Britton is Rh negative. She gets pregnant, and she's now my patient. I'm going to draw her blood. I'm going to identify her blood type. I say, Britton, you are Rh negative, and here's the issue. Your immune system could go on the attack and kill your fetus. And Britton says, but I want my baby, and I say, I want you to have your baby too. Here's what we're going to do to prevent that from happening. I'm going to give her a shot. And Britton says, oh, no. So I took physiology. I'm aware of how the immune system works. This is my first pregnancy. And the Rh factor is not very antigenic, she'll say to me, and I will say, that's awesome, you're right. But Britton, is this your first pregnancy? And she says, yes. And I, in my head, go, she's lying. She's really a whore. This is her 10th pregnancy. I mean, I'm being facetious for the sake of keeping you awake. So the idea is, how do I know for sure it's her first pregnancy? She could have been pregnant before, and her immune system has already been primed for this, sensitized, because there's been mixing with the fetus blood from the previous pregnancy. I don't know that for sure. I'm going to say, I'm going to give you this shot. It will help prevent your immune system from attacking your fetus. Then she says, actually though, I'm pregnant with Cole's baby. And he's Rh negative. So we're good. I don't need this shot. I hate needles. And I say, you need this shot. I highly recommend it. She goes, but I just told you, Cole's the father. He's out in the waiting room. You could blood type him yourself. I say, fine, that's awesome. I blood type Cole and say, yeah, he is negative. You're right. He is negative. Not the first time, no. Happens a lot, more than you think. Some people have so many sexual partners within a certain short amount of time, they're really not sure who the daddy really is. I know this for a fact because the same cousin of mine, yeah, she had a hard time figuring out who was her daddy, or who was the daddy of one of her 6 kids. She's got different dads.
Oh.
There's not a lot to do in the Midwest, is how I figured this out. Not a lot to do, except to eat each other. I don't know. Anyway, especially during the winter months, it's too cold to do outdoor activity. I don't know. Anyway. So I say, no, you still want this shot. And here's what the shot is. This is going to blow your mind. So ABO incompatibility, very real, very statistically relevant, but clinically relevant, we don't care because time is on our side. But this HDN incompatibility, some of you said, well, it only matters if it's the second pregnancy. All right, let's entertain that. Here's Britton. Statistically speaking, she's probably going to get pregnant with a person who is Rh positive, and her fetus will be Rh positive. Her immune system is not sensitized yet. Blood is not mixing until her delivery. Then her immune system says, if it could talk, oh my gosh, that was in us this whole time, we didn't know. Fool me once. Right? Shame on me. But I'm going to be ready the second time. So she gets pregnant a second time with an Rh positive baby. Her immune system has now been sensitized, making antibodies against the Rh factor. Her second pregnancy is at a risk for this agglutination to happen in vivo. So what do we do to prevent that? And do we really ask the person, is this your first pregnancy or second or third? We don't care. If I find out you're Rh negative, I am going to do my best to educate you that you need to protect your fetus from your own immune system. We need to prevent this from happening. And here's the injection I give. The injection I give is anti-Rh antibody. The very thing Britain will make, the very thing that can cross the placenta and attack her fetus, I give to her. It's the same antibody. Oh, there it goes. It's the same antibody. If it's the same antibody that I'm injecting, can it cross the placenta and get into her fetus? Yes. Will it attack, potentially, her fetus's red blood cells? Yeah. Are we smoking pot now that it's legal? Why does this immunization work? It's the same thing we don't want Britain to make. It's the same identical antibody. How does it prevent HDN when the same antibody, if her body makes it, will cause HDN? And that stands for hemolytic disease of the newborn. And here's how it works. I'm going to pick on you, Roman, since you're wearing this. Students from the past will tell you never wear a hoodie sweatshirt around here, because you will be used as a prop. So here you go. Let's pretend the Rh factor is Roman's hair. Britain's immune system will enter her fetus and attack anything that has this hair, right? The Rh factor. I inject into Britain the Rh antibody. Here's how it works. It will go find any fetal red blood cells in her body. They can escape. They're not supposed to get in her body, but they can. You just heard me say that we can have mixing. So the injection I give finds red blood cells from the fetus that are now circulating in mom. The antibody I've injected finds the Rh factor on those fetal red blood cells circulating in mom and binds to it, covering up the antigen. That's what antibodies do, right? They bind the antigen. So if the antigen is now covered by the injection I gave, Britain's B cells, if they could talk, they would do this. I thought I saw something over here that I should, I guess not, nothing to see. And they go on their way. Never get sensitized. They're neutralized. The injection neutralizes fetal antigens so that her B cells don't get activated like you saw in the previous picture. And we give this around 28 weeks of gestation, which is a little bit before the Rh factor starts to be expressed. And we will give this injection every time we suspect fetal blood mixing with mom, during any procedure where that can happen, like an amniocentesis. Hours after delivery even, we can give multiple injections for the same pregnancy. And students then say, well, if we give too many, could that have adverse effects? And we've done those studies, and it turns out it does not have adverse effects. In the end, it helps prevent adverse effects. We give this. You want to get this Rh factor antibody injection, all right, ladies? Okay, because it's not about you when you get pregnant, it's about that healthy little fetus. This is how we prevent HDN. If you two end up being selfish and your body has an immune response to Rh factor, this is what can happen to your babies. They will have profound agglutination. They can have hemolysis. Now you're talking about reduced red blood cell count. Your baby at best will be born with anemia. And even worse, the side effects of red blood cells being lysed leads to a lot of bilirubin, and excessive bilirubin kills neurons. Now you're talking about your baby being born with a mental deficiency. When neurons are killed because of excessive bilirubin, this is called kernicterus. So what can we do to treat HDN? Clearly we can give a blood transfusion to the baby. We can even put them under Billy lights, which is, it's a tanning bed, that's what it is. And the tanning bed helps convert the bilirubin into a more water-soluble form, and that's easier for the baby to eliminate as waste. You will learn more about this process of bilirubin synthesis and removal at a later date. We can even give an intrauterine blood transfusion if we have to. Those are very tricky to do, but we can, and we have done it. If it means that the baby is born with a better prognosis, better APGAR score when they're born, we're going to do it. So what are all the things that can happen in utero and after the baby's born? Clearly hemolysis, red blood cells being destroyed. That's how we carry most of the oxygen. If the baby is developing, then it needs oxygen for all of its developing organs. They are going to be compromised. Organs that remove dead or dying red blood cells that are under attack, like the liver and spleen, will be overly worked and they will enlarge. So there will be hepatomegaly and splenomegaly, which means very enlarged organs. This is a picture of a spleen, but not from a baby. That's from an adult, because that spleen is about the size of a baby. That's how enlarged it is. And you heard me talk about kernicterus, which is death of the neurons. We don't want our babies to be sent home with severe mental deficiencies if we can prevent it, if we can avoid it altogether. So how do we prevent? And who is it that we focus on? Mom. And we give the mom the antibody injection. That's how we prevent. How do we treat if HDN does occur? And who are we addressing? The baby. How do we treat it? Blood transfusion. Now, I'm going to leave you with this, just to get you laughing before I dismiss you. I had a student who did not pass physiology the first time, and when he came back for the second time, he slept through the lab every time. And he would pull the whole stack of paper towels to him, and he would use it as a pillow every time. He would just sit down, pull it, and he'd fall asleep front row every single time. I'm giving this lecture in lab. He's sleeping through most of it. I get to this slide talking about blood transfusions, and I say we can even give the fetus a blood transfusion intrauterine if we have to. And I said we replace the fetus or infant's blood with O negative blood, so that if mom's immune cells are in the baby, there's nothing for her immune cells to attack. There are no antigens. All he heard was we replace the infant's blood with O negative. He raises his hand, because now he's awake, and he says, wait, we replace the infant's blood with O negative blood? And I went, yeah, if you had been paying attention, this is what you would have realized. And he kept having an issue with it, and I couldn't figure out why. He says, really, we replace the infant's blood? I was like, yeah, we replace the infant's blood with O negative. Why are we? And it took me a while, but then I realized the movie he was playing in his head. He thought we drained the baby of its blood, so he had images of like, and then we fill it back up with blood that's O negative. That's what he thought. And I was like, there's a reason why you didn't pass this class the first time. Bye, I'll see you Wednesday.